I'd like to start this section with a visualizing exercise from the last section. The picture on the right is a diagram of a process that occurs at an electrode in a voltaic cell. So we see large spheres on the left, and let's call them the solid. We see what happens is the large spheres are turning into something smaller. So that would probably be the cation. And is this an oxidation or a reduction? Well, we learned about balancing half reactions, and we would have to put electrons as a product. That makes this an oxidation. Is the electrode that they show, is it an anode or a cathode? Well, think about the crazy thing we used to remember this. Both of these start with a vowel, and it's definitely a anode. Why are the atom spheres larger than the spheres in solution? Well, remember, the radius of an atom is always larger than the radius of a cation, and that comes to us back from chapter 7 and 10. That gets us started. So here's this new section, cell potentials under standard conditions. The best way to tell you about a potential is to say, first think about a waterfall, how water goes down when the water is flowing. The same thing happens with electrons. They flow spontaneously through an electric circuit because of a difference in potential energy. Think of the top of the waterfall as having a high potential energy. Think of the bottom of the waterfall having a low potential energy. At the anode, what we have, and I'll just use it this way, a metal as a solid goes to form a metal cation in aqueous solution and an electron. So essentially, we want to watch how the electrons flow. This electron will flow from the anode to the cathode. And what's happening at the cathode? We have a metal ion. It is going to pick up an electron and make the metal again. So that's how we explain, for now, in Chemistry 1220, what is a cell potential. I didn't make it large, but what I want to pull your attention to is I put kind of a thing, I said same term. If I have a voltage, if I have E cell, if I say EMF, if I say potential difference, if I say cell potential, if I say electromotive force, in 1220, those mean kind of the same thing. In a higher level course, they would have a very specific meaning, but I just want to point out to you. In our next slide, it's very simple compared to a lot of the other things we've done. This is called a standard reduction, and it says half cell potential. By convention, we will always write a reduction reaction, and there is our reduction, and it will have assigned to it an E0 reduction. That's its half cell potential. We cannot find that unless we have the entire redox process. We must have an oxidation, we must have a reduction, and that's really what this section describes. So my next bullet says, it is not possible to directly measure the potential of a half reaction. Before we leave this little section, standard conditions, they're kind of looking the same for everything, aren't they? 25 degrees centigrade, 1 molar aqueous, and 1 atmosphere, okay? So that's a standard reduction potential. The other thing we do in this section is we define a reference half reaction. And the reference half reaction is defined as the standard hydrogen electrode, and you can see its picture over here on the right. In analytical chemistry, they go much, much deeper. We just want to tell you that this equation represents an SHE, and notice that it has been assigned a reduction potential of 0, okay? If I look at the next picture, and I did this in the middle, I said maybe this is better to put it here. This is the key equation. We use a convention where we take the reduction potential of what's happening at the cathode and subtract from it the reduction potential of what's happening at the anode. We use the numbers that you will soon see directly in a table. Well, where did this come from? If you put a strip of zinc metal in acid solution, this is from the previous section 20.3 showing the cell, you would observe certain things. You would observe that the zinc is losing mass, you would observe hydrogen bubbles, and you would observe a cell voltage reading of 0.76. When I wrote those down, I said, like, how are they going to understand this? So this is what we mean by zinc losing mass. If I were to reweigh the anode, which we used to do always in lab, you would see that. If hydrogen bubbles are observed, well, that's the picture here over on the right-hand side. There are the little bubbles. And if the cell voltage reads 0.76, that would be up here in the picture. So we have these pieces of information. We have an E0 of cell. We have defined the 0 as the cathode. We have defined the anode as the zinc. And when we crunch those numbers together, we get a value 0.76 volts. Therefore, if I want to write the potential for zinc, I would use that value. And that value is going to be found in a table that we're soon going to see. So I guess what I missed here is what they put here on the bottom. See how the zinc is undergoing an oxidation. See how the hydrogen is undergoing a reduction. This is the classic example, but this is every example. If there's going to be a redox process, there'll be a cathode and an anode, and one can use the values that have been obtained by others in order to solve some additional problems. So here is the table. All of these were determined by observation. In the lab, you used to take different metals and you would cross one to the other and make some decisions. Well, the samples were like from the Civil War, so in a way it's good we're not doing that. Note where hydrogen is. It is sitting right there. And what does the placement in the table signify? This table, and it sits here. Here we have at the top our fluorine. Here we have at the bottom our lithium. And so these are all standard reduction potentials. Well, that's on the next slide. If I revisit that zinc strip in the copper sulfate, I can measure a potential, okay? So let's try to show you where those values did come from. I have the copper going to form copper 2 plus going to form copper. There it is. I have the zinc, and it's going to form zinc 2 plus. So this in the equation is the reduction. This in the equation is the oxidation. And when I wrote them, I wrote them both as reduction potentials. That's really what I did. I guess the point I'm trying to make here is this process is the reduction. This process is the oxidation. I take the values from the table, okay? Oxidation is a minus 0.76. Reduction is a 0.34. I do not change the signs, okay? So this comes from the table, and I'll say no sign change, and that will give me the potential for the cell. Notice 1.10 volt. That would be what we would actually measure in the lab. So that tells you how to work with the numbers on the table. It was like a chicken and an egg. Which do I do? You look back at water at first. The next one says, why don't we tell you why things sit where they do? So I pick fluorine at the top and I put lithium at the bottom. And here we can say, fluorine, you know it's diatomic, you know that it is S2P5, you know that it wants to become S2P6. That makes it the most easily reduced species. And notice it has a very positive E0 reduction. Lithium, the thing that's your battery that goes back and forth, that is the most difficult species to reduce, and what it has is a negative reduction potential. So here we have a positive for the most easily reduced and a negative for the least easily produced. So here's the point on the bottom. The more positive the E0 value for that half reaction, the greater the tendency for it to be reduced and to oxidize another species. Now, I'm really limited by time on these videos, and I like to go back and forth, but I really don't think I can. So everything we'll talk about will be coming to take place in water. But again, this is to show you the link from back in 1210 when you learned about the atom and its chemistry. Notice how we're seeing this in electrochemistry. So there is a table in your book about oxidizing and reducing agents. You will either solve problems using numbers that they will be given, or they will give you equations that you can match about what does what. Think back to chapter 4 in chemistry 1210. We did have some problems where they gave you equations and you worked backward with the activity series. The same thing can happen here. But the thing I want to point out is the easiest to reduce is the strongest oxidizing agent. The most difficult to reduce is the weakest oxidizing agent. My last slide here has an example. Let's say I want to consider these three cations. I want you on a midterm to tell me what's the best oxidizing agent. Or I might ask you what's the best reducing agent. What you want to do is you want to write down their E0s. It might take a little bit of time, but trust me, just do it. What I did is I put them in order. I put the most positive at the top and I put the most negative at the bottom. So if I'm trying to define what is the oxidizing agent, that'll be a question I'll ask on the midterm. That is the most easily produced. Notice I have my positive, my less positive, and even my negative. That tells me these cations, because they can undergo reduction, are the most easily reduced. The other thing they ask is about the reducing agent, and that would be the most easily oxidized. So here, what I did is I put my negative value first, and I went all the way towards the positive values. Students have struggled with this traditionally. It's something that you just have to sit down and think about. When we talk about an oxidizing agent, it is a cation. When we talk about a reducing agent, it will be the metal. So again, the answers they present on a midterm, they can be tricky. Please don't fall for the trap. On the bottom, here is something that when you work in a lab, just like oxygen or CO2 could influence your values in a titration, oxygen can also have an effect on a redox. Notice it has a pretty positive reduction potential. That means it can readily reduce things often when they are not desired, or oxidize things when they are not desired. Again, that would be like a word question. And I wanted to put in some visualing exercises. It would just be too long. So what there will be for chapter 20 is all of the visualizing exercises worked through in a separate video to make points about electrochem. This is a really important chapter because it sums up practically everything in chemistry 1210.